Hello, welcome back. So we are going to continue our discussion about uh, the big O time complexity analysis. In this section, we are going to compare different search algorithm, their time complexity. Okay, so we start with the simplest case. So the sequential search is big O. So this is the code snippets. So the for this sequential search, linear search, okay. And so this for loop, it will loop n plus times. Okay, so we are already quite familiar with the number of times for loop statement. And within the loop, because I will not run all the way to n, okay? So that's why it's one times less than the loop. And the return statement, it will only be executed one times. So it's one. And we sum all of that, we can come up with Tn is 2n plus 2, okay? So 2n plus 2, if you recall previously, we said polynomials, we just take the highest degree term, okay? So it's n, so this is linear. So we can simplify its big O as order n. Okay, so that's the time complexity. So next, let's see what's the different cases. Okay, best case, average case, and worst case. So we can clearly see from linear search. So the worst case is the target you are looking for cannot be found. Okay, then definitely it will run through all of the loops. Okay, so it's order n, okay. And the best case, so best case is at the starting of the iteration, is it, and you find it. The item is at the very beginning, okay. So then the total number of execution is 2, so it's a constant time. So the best case. So average case, so it's just the item positioned randomly in the middle. So it's approximately so n over 2, so half of n, so it's still linear. That's it. So, and if you recall at the very beginning, we said that normally when we discuss, we use a worst case as a benchmark. Okay, so we can see linear search is order n, okay. Okay, next, let's come to the next search. It's called binary search. So binary search, and keep that in mind, it must be for sorted list. So all the items must already be sorted, okay? So for example is like we can see, it's suppose you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is it like those 12 number? And suppose you want to find, assuming it's 2 is our target. Okay, then in this case, the binary search is, so here we have 12. So we first need to find the middle item. Okay, so 12 divided by 6. So it's probably, let's take 7. Okay, so this is a middle item. Okay, and then you're going to have so you're going to compare target with the middle item. So compare. So then you find 2 less than 7. Is it 2 less than? Because this list is already sorted, so for sure you know that the item must be positioned in the left part of this middle item, and you can drop off the right part. Okay, you can drop off the right part. And then within this, so in this left part, then we are going to do the same thing. You split it into half. As if we find the middle item. So this is the middle item. Then you compare target with the middle. You can see, okay, 2 is less than 4. So for sure, it's not going to be in the right half. So it must be in the left half, okay? Okay, for the left half, then you find the middle item, middle item, and then you compare, okay, it is the item. Both are equal. Then you find it. So with 3 comparisons. So here we have 3 comparisons. Then you find it. But of course, this list is already sorted. And for 2, then you can clearly see, okay, you say, okay, if I do linear, then maybe I just need 2 comparisons. But you think about if you're going to find something towards the middle, then the comparison will be fewer than you do the linear comparison. Is it? So we can see that for binary search, because the item already sorted, so when you try to find some target, each time you drop half of the list for search, the kind of. So definitely the comparison is going to be fewer than you do one by one comparison. Okay, then next, let's take a look. How do we analyze the algorithm, okay, for binary search? So as previously, as if whenever we try to do analysis, we do statement by statement analysis to find out how many times each statement is going to be executed for an input size of n, okay? So for this statement, definitely one time, no doubt, one time, okay? So this while loop, then if you remember what we just discussed about the algorithm, so it's kind of you need to do split by half. Okay, find the middle, then split half, find the middle. But we don't know how many times. So you can assume, okay, it's k times of split in half. But the question is, what is this K? Is it? So let's see. The idea is you keep short the size of uh, uh, the the sublist that you're going to search. Is it? So so initially your input size is n. Is it? So then you divide by 2. So that's the first split. And then you use this divide another 2. That's the second split. And then you do another 2. That's the third split. Is it? And so totally we have k. Is it? Okay. So then the idea is n over 2 to the k times. Is it? So so the ideal scenario is then at this point, the sublist, you will only have item that's less than 2. So you will only have that one item. But have that one item, you either find it or not find it. Okay. So it is either that item or not the item. Suppose the target is not in the item, then okay, compare it's not. Then You cannot find it. So we can get to this relationship. And then we get this relationship, then okay, we can times 2 to the k on both sides. Then we can get n less than 2 to the k plus 1. Okay. Now with this, how do we find the k? Is it? Okay. So then it's what? It's basically this is 2 times 2 to the k. Okay. And you can let this 2 divide 2 on both sides. So n over 2 less than 2 to the k. And then we can take log 2, is it? Take log 2 on both sides. Then the right side change it to k. And this is the left side, is it? So basically, then what is k? So k, you can take the integer part of it. Part of it. So basically, this is, we can take it as n, okay, as n. And you take the integer part of it, so k is the integer part of log 2n, okay. So we can find the key, okay. So that's, but the loop itself, because it's if you recall, we have one extra loop, okay, for that exact equal cases. But within the loop, then it will be like k times, is it? And k times. So anyway, all of this is going to be around k, cannot, so the degree will not beyond, will not go beyond k. So basically, we mean it's this linear k. It won't go beyond, is it? So then we can conclude, so no matter what, the total summation of this algorithm is going to be a polynomial of k. So k is what? K is log 2n. Is it? So we can conclude, okay, binary search is big O is order of log 2n. Okay. And then as our example also shows, is that because the log 2n, it runs much slower than linear. So definitely we can see binary search is more efficient. We can conclude it's more efficient, is it, than linear search, okay? Because of this big O, we prove it. So that's how we come up with the analysis for binary search. So it's log 2n. And in this section, we are going to compare various sorting algorithms. If you recall, in chapter 17, we discussed different sorting algorithms. Okay, so let's do a comparison among them. So we start with selection sorting, okay, algorithm. So it has a nested loop. So the outer loop, we can see it's n times, okay. So the inner loop, so this based on I, okay. So when I is 0, we can see the inner loop will loop n times. When I is 1, then it will loop n minus times. When I is So this is when I is 0, I is 1, and I is 2, it will, this inner loop will loop n minus 2 times. Okay, so when I is n minus 2, then it will loop twice. So total number of times it will be executed for the inner loop statement itself is you are going to add all of them together. Is it? So the result for this summation is going to be n times n minus 1 divided by 2. Okay. So that's the inner loop statement itself. Then we can clearly say that this n times n minus 1 divided by 2 is a polynomial. So the highest degree term is n square. Okay, n square. So it cannot go beyond n square. So we can clearly then conclude that all of the inner loop will not go beyond n square. Okay, and this outer is linear. So from the analysis, we don't need to do the one by one and add them together the exact. Okay, we can conclude, we can see. Okay, the polynomial term, the final result, the polynomial term will not go beyond n square. So we can conclude that for this selection sort, its time complexity is order n square. Okay, it's a quadratic one. So that's for the selection sort. Okay, so it's n square. Okay, next let's take a look at the bubble sort. Okay, so bubble sort, then this will be just one time, and this loop, generally speaking, okay, it will be n times the outer loop. And then the inner loop, similar, if you recall, is that because each time it excludes one item from sorted, is that so unsorted part, it's decreased by 1. So that's why for the inner loop, it will go from n all the way to 1. Okay, so it's a summation. So summation from summation I from 0 to I from 1 to n. Okay, so the result will be n times n plus 1 divided by 2. Then similar concept for the inner comparison and swap, is it? So it will not go beyond this. So the polynomial and we summation of this, then the polynomial highest degree term will not go beyond n squared. Okay, so then we can conclude, okay, for bubble sort, then the time complexity is n squared. But if you recall, and this is just based on this algorithm analysis, assuming for the loop, it will go through all of its iterations, okay? But there are some cases that will not go through all of the cases, not go through all of the iterations, okay? So the best scenario, so best case, is it Best case is it's already sorted. So if it's already sorted, you know, so here, okay, false, then this is true. Okay, so we are going to go to the inner loop. Is it for the inner loop? Okay, and you go if there is no, so here, if there is no swap, no swap, then you won't get to this statement, is it? So, uh, so the sorted will be true. Then when you come back to the second loop, so the loop will be terminated. Is it? But you still go through this inner loop, and the inner loop will be n times. Is it? So that's why in the best case, the order is linear. Okay, linear. Because you still need to do the comparison for the whole list. It's just if there is no swap that you detected, okay, then you stop the outer loop. So that's the best case. And the worst case is in reverse order. In reverse order, then the outer loop will go through its full iteration. The inner loop will also go through its full iteration. So it will be n squared, okay? And the average case, then it's just randomly located. Okay, so it's also going to be n squared. So that's regarding bubble sort. So but for bubble sort, we have three different cases, okay? So the best case is the list is already sorted, and the worst case is the list in reverse order. Next, let's take a look at how we analyze quicksort. And if you recall, quicksort is we implemented as a recursive approach. So recursively, okay, so how do we do the analysis? Is that, and it's going to be recursively executed, and it involves you split around the pivot. Okay, and so because here it involves the split around the pivot. So totally how many times it will be split. And if you recall, this concept is similar like the binary search. Also involves split by half. This so here is also involves split. Okay. So if you recall, as we derived, okay, split by half, totally how many times we are going to split? Log 2n, okay, with the input data size is n, it's the number of times that's splitted. Okay, so log 2n, okay. And so that's because this is a recursive, so it will call split, recursively call. So totally log 2n. But if you recall the split itself, okay, also involve a loop because it do the scanning, is it the scanning from left, from right, from left. Okay, so that's linear. Okay, so that's n. We can consider n. Okay, so then based on this analysis, so total number of times split is log 2n, and the split itself is n. So then we can derive, is it the maximum, it won't go beyond the polynomial, the highest degree for the polynomial will not go beyond n times log 2n. Okay, and because of this, then we can conclude that its time complexity is n log 2n. Okay, but so this is for the quicksort, but there are also different scenarios, the best case. So best case is each time your split is kind of by half. Okay, so split by half each time. Okay, and we can also see the average case. Then it's not exact by half, okay, but it's you still have two sublists, okay. The worst case. The worst case is the sublist, its size is always you only have one sublist. One sublist for each split. For each split. Okay, then in this case, because you are not going to split by half, is it? So the number of times you are going to do split is n instead of log 2n. So not log 2n. Because you basically don't have splits n, okay? And the split itself is also n. So that's why in this case, it will be n squared, okay? Versus best and average case, it's n log 2n. So quicksort, then if you have best case or average case, it's n log 2n. Otherwise, it's similar as it's similar as the selection sort or like the bubble sort, okay, for the worst case. So that's regarding quicksort. So generally speaking, quicksort is faster, okay, because generally the item is randomly positioned, okay, and when you do sort, it's n log 2n. But recursive also has a price to pay, okay, for the time complexity, efficiency, because it involves a recursive call. And the recursive, each time you call the recursive function, it will put the function call. So function call. So the function on the stack, function on the stack, function on the stack. Okay, just think about if your data size is very, very large, it's quite large, then you need to have the stack, the runtime stack size, memory size also very large to hold it, is it? So we see like the quicksort, it get time efficiency, is it time efficiency with the price of the memory usage. Okay, so that's for the quicksort. Okay, next let's take a look at the merge sort. And merge sort, if you recall, is also recursive, recursively implemented. So it also involves split by half. Now we kind of know if it involves split by half, the total number of times, then split by half will be done as log 2n. Okay, it's always the case now. Okay, we know that. And then let's see. So then it involves the merge itself. Is it just like a quicksort split? So the merge itself, if you recall, so it have the two sublists. And then you need to order them. For all of the items from the two sublists, you order them and then put them in a temporary array. And then you copy the temporary array to the original array. So for this operation, it needs n. For this, it will need n. Okay, yeah, clearly. And then, so basically, we put all of them together. So considering the polynomial order term, it's still n. It cannot go beyond n, okay? So the merge itself operation is n. Total number of times split, it will be log 2n. So total it will be n times log 2n. So we can clearly see quicksort is still quite efficient, okay, compared with like selection sort, other sorting algorithm. Okay, so that's the analysis about merge sort. So both merge sort and quicksort, overall speaking, for the random large number, we can see the time complexity, the big O is n log 2n. Okay, then next, let's see the comparison among of the sorting algorithms, okay, that we just discussed. And also let's compare them in different cases, for the best case, for the average case, or for the worst case, okay. For the best case, we can clearly see the winner will be bubble sort. So it's linear, okay. Next, it will be quicksort and merge sort. So this is number one, this is number two, and the worst is the slowest will be selection sort. Okay, and then for the average case, we can clearly see quicksort and merge sort is number one, and bubble sort and selection sort, and both of them are quadratic in square. Okay, so it will take more time, much more time, okay, compared with quicksort merge sort. And for the worst case, yeah, we can see for merge sort, it's still take the lead, okay, number one, but for all of the other case, they are the same, okay. We can see merge sort overall has pretty good advantage among all of those sorting algorithms. And in our textbook, we also have an example in Java code. So it's Java big O example. And in that example, we generate quite a large random numbers. So all of those are random numbers and randomly placed, okay. Then we run the above four sorting algorithm and measure them, the running time, okay, in milliseconds. And for bubble sort here, and of course this is running on my machine, okay, in different machines, the result is going to be different. So for bubble sort, it's this much of millisecond for selection sort and for quick and merge sort. So from the this running result, we can clearly see, yeah, quick sort and merge sort runs much, much faster than bubble sort and selection sort. Okay. And here you may also say, okay, why selection sort seems faster than bubble sort? So maybe this batch of random numbers, maybe the kind of not averagely distributed, maybe kind of more close to reverse order. Because if you recall, the reverse order is it then for the bubble sort, mm, uh, it takes the longest time. Okay. Okay, so that's all of the discussions about time complexity analysis. So the big O, how do we derive the big O? And we also saw various algorithm, like search algorithm and sorting algorithm. Yeah, so that's about this chapter. And oh, and before I forgot one last interesting thing is about that national park. Okay, if you recall, so that national park is the Mammoth Cave National Park, and it's in Kentucky. Okay, it's quite grand. Yeah, so that concludes this lecture, and see you next time.